Good morning, dear students. Today we are going to determine the isoelectric pH of a given amino acid using titration method. First, we need to understand what is isoelectric point. Isoelectric point is a point of pH at which a particular molecule didn't carry any electrical charge. That means its positive charge and negative charge will be equal, same. So in that way, that molecule exists as neutral without carrying any net electrical charge. That point is called isoelectric point. Clear? Next, we need to have an idea about amino acid regarding its molecule structure, which are molecules present, what is its nature. So that I am going to explain to you. Here shown the structure of a simple amino acid, that is glycine. In this picture, we can see this amino acid is composed of a basic amino group and an acidic carboxyl group. That means it has acidic as well as basic group in it. And also, as it possesses a basic and acidic group, it can either donate proton as well as it can receive proton. That depends upon the pH. Okay. So, whether that amino acid to donate or accept proton, that is determined by pH. Okay. And if such an amino acid, if it is subjected to an acidic medium, that amino acid will gain protons, that is H plus ions, and they become protonated when in acidic medium, that means at low pH. Okay. Then if such an amino acid is placed in a basic medium, then it will lose protons. That means it will get deprotonated. So in high pH or in a basic medium, ionizable group present in the amino acids will lose its protons. There is another situation. Then we need to understand about pKa. pKa is a specific constant value for all molecules. It can't be changed. For explaining the nature of pKa, I am giving you one example. Example means, suppose pKa you imagine to be a mountain. This is pKa. And the air that's swirl around, this mountain is pH. If that's a situation, we know that the mountain will not change. It will stay as such for long. But the pH, or otherwise the air, we are comparing pH to the air that's swirl around the mountain. It can be cold, it can be warm, that only can change its nature. In the same way, whatever pKa molecule possesses, it can't be changed. Okay. Then how the ionization is possible? That ionization is possible by changing the pH. Okay. By changing the pH of the medium, then we can ionize that amino acid. I think it's clear. Next, we need to by heart or we need to know three equations. Three equations we need to know that I am going to show you next. First equation is that situation when pKa is equal to pH. pKa, when it is equal to the pH, then in that amino acid, the number of protonated factor will be equal to deprotonated factor. The number of protonated factors will be equal to the number of deprotonated factor. That is equation 1. What is the condition? When pKa is equal to pH. Next situation, when pKa is greater than pH. If pKa value, if it is greater than pH, then that time in that amino acid, the number of protonated factor, it is more when compared to deprotonated factor. That is equation 2. Then and next third situation. What is that situation? Here the pKa value, this pKa value is less than pH value. Okay, in that situation, in that particular amino acid, the number of protonated factor will be less than that of deprotonated factor. That is equation 3. Sorry, not 2. Equation number 3. Okay. For easily memorizing all this equation is very easy. To write pK always first in all the 3 equation, then only need to write pH, and also in the remaining part, first you need to write the protonated factor, only then need to write the deprotonated. Then regarding the symbol, that relationship, equal, here also equal, here is the greater, here also greater, here is less, here is less. That way we can easily memorize also. Next, I am going to show you the structure of glycine, the simplest amino acid. It has 2 ionizable group, the carboxyl group and amino group. And the pKa, approximate pKa of this carboxyl group is 2, around 2. And the approximate pKa of amino group is around 10. Okay. Then one more thing we should know, that the protonated and deprotonated form of carboxyl group and amino group. Carboxyl group, its protonated form is COOH itself, and deprotonated form is COO minus. And regarding the amino group, the protonated form is NH3 plus and deprotonated form is NH2. Okay. Next, we need to consider different situation having different pH. First, we are starting with the pH 1. pH is equal to 1. In such a medium having pH 1, we have an amino acid, and we know that it has carboxyl group and amino group. What will happen to those groups? That we need to think. And for that, first we need to take the case of the carboxyl group, because pK1 is always referring about the carboxyl group, acidic group. So, if consider the case of carboxyl group, we know that its pKa value is approximately equal to 2. And then we need to look up to these 3 equations. What about the value of pKa value when coming to this equation? pKa value, we know it is 2, and pH it is 1. It is not equal, so this equation is not applicable. Then coming to the next one, pKa is 2 and pH is 1. pKa value greater. Okay, this situation is applicable with regard to this condition. So, according to this equation, if pKa is greater than pH, what will result? The number of protonated factor will be more than the deprotonated factor. So, the carboxyl group will exist in COH form, that is a protonated form. Then we need to think about what will happen for this amino group. Amino group. We know that its pKa is approximately equal to 10. Then we need to check with the three equation. pKa it is 10, pH is 1 is not, and in no way it is equal. We can't use this condition. So next one, pKa we know it is 10 and pH is 1. pKa is greater than, that is situation we can apply. That equation we can apply here. According to that, if that situation persists, that amino group exists in a protonated form. Protonated form is NH3 plus. So at pH 1, the amino acid has net positive charge, because here it carries a positive. By that way, that amino acid exists with a positive charge. Okay. Next, we are taking the case when the pH is 6. And at this pH, what will happen to COH group? COOH group, we know its pKa is approximately equal to 2. Then we check with the equation. First equation is not applicable because pKa 2 is not equal to pH 6. So it's not applicable. Then coming to the next one here, the pKa we know it is 2. It is greater than pH 6. No. So that equation also not applicable. Coming to the third one, pKa is 2 is less than. Okay, this situation is applicable. Under that situation, COH exists in deprotonated form. Deprotonated form. Okay, so COO minus is the deprotonated form. Okay, then regarding what will happen with respect to amino group. Amino group, its pKa we know it is approximately equal to 10, and first situation is not applicable. Second, pKa it is 10, it is great. Okay, this is correct for amino group, and under that situation protonated factor will be more. Means that amino group exists in protonated, complete protonated form. Is protonated form, we know it is NH3 positive. So the number of negative and positive charge is equal, and so at that pH this amino acid exists as a sweeter ion. At this pH is its isoelectric pH, isoelectric point. Okay, next I'm going to tell about another situation, that is with the pH is equal to 11. In that medium, what will happen to the carboxyl group of that amino acid? Carboxyl group, we know its pKa is approximately equal to 2. No way first equation is applicable. Coming to second, pKa that is 2 is greater. No, it's not applicable. Coming to the last one, the pKa that is 2 is less than pH. Okay. Under that situation, the COH exists in a deprotonated form. Deprotonated form is COO minus. Okay. Then regarding the amino group, its pKa roughly we know it is around 10, and first equation is not applicable. Second, pKa that is 10 is greater than pH. No, it is not applicable. Coming to the third one, pKa that is 10 is less than pH. Okay, at that situation, that NH2 amino group exists in deprotonated form. Deprotonated form, we know it is NH2. It is not having any charge. It is neutral. So at that pH, the amino acid is carrying a negative charge. Okay. And finally, I am concluding the situations into three statements. At pH 1, amino acid carries positive charge, and at pH 6, amino acid exists as a deuterion, and at pH 11, amino acid is carrying negative charge. And the equation for finding the isoelectric point is pK1 plus pK2 divided by 2. And pK1 and pK2 value we can determine from the graph plotted using the titration values. And also along with that, we are using an indicator to easily understand that change in the pH in the medium. The indicator that we are using is diamond blue, and what is its behavior towards different pH range is that at a pH around 1.2 it exists in red color, and as it moves as the pH raise towards 2.8, that red color become pale and become yellow. And coming to pH 8, and as it raises to 9.6, that pale yellow color will turn to blue. So in that way we can we can detect in observation wise, we can detect the change in the pH in the medium during the titration. Okay, so next we need to understand what are the materials required. Here we have taken one normal HCl, one normal NaOH solution, then one normal glycine. How to prepare a particular normality solution that I already explained in one other video. Its description I will give at the end of this video. And the thymol blue indicator, pH meter we need, beaker and bureau. Okay, let's start the practical. Here we have a calibrated pH meter, and also in the small beaker we have taken one normal 10 ml glycine and one normal 10 ml HCl solution. And to this I am going to add thymol blue indicator. After adding thymol blue indicator, we need to stir the solution and to note the initial pH value. Okay, then after that we need to add 1 ml of one normal NaOH solution sequentially until we get a pH value of 12 in the pH meter. So, after adding each 1 ml of NaOH solution to this beaker, we need to stir it and to record the pH value displayed in the pH meter. Okay. This is the titration value that we got during the titration. And as we look to this values, we can see the change in the value after a constant range of value as here, and that can be pK1. And again there is another change that is that we are considering as pK2. And these two values, as we substitute in the equation, we know that equation of isoelectric point is equal to pK1 plus pK2 divided by 2 is equal to 2.3 plus 10.8 divided by 2, which is equal to 6.5. This is the isoelectric point. Anyway, the isoelectric zone of glycine extends from pH of 4.5 to 7.5. I think our value also correct, even if accurate isoelectric point of glycine is 6. Okay, then I am going to show you a graph that we plotted out of these values. This is a graph by taking the x-axis as OH minus equivalent and the y-axis as the pH value. We can plot the graph like this and we will get a graph in this form, and we can note that pK1 value and pK2 value here. Okay, and this is the practical for finding the isoelectric point of glycine. I hope that with this you really understand the procedure. Thank you.
I'm an icon, man. And my girl about a 10. I should fuck her in a Benz.